Okay, so in the next 30 or 40 lectures, I will be talking about metric embedding. So naturally, there are three cornerstones. One of them is Jensen-Lindenstrauss lemma, which I prove in this lecture. The other one, idea of for general metric, not just Euclidean, Bourgain and many researchers especially in France and Israel, very great researchers, and most of them are mathematicians and computer scientists. They try to extend this idea to general embeddings, and we can embed into LP in ultrametrics into any space that is interesting and has, for example, ultrametrics has intuition, has some meaning in biometrics and also genetics. And also Kuratowski embedding, which embeds your metric space into a Banach space, for example, L infinity of R, the space of functions. And so in order to use all the things that we know from Banach space, because it is it gives us a geometric intuition, and that's why Kuratowski is very interesting. And classical things like Gromov-Hausdorff theorems and all of them are well explained by the guy called Nauer. So in this lecture, I only focus on JL lemma. So principal component analysis, multidimensional scaling, we never get guarantee on point-wise distortion. We don't even talk about it. And if we have x1, some endpoint data, x1 through xn, and each of them is in RD, we call it projection because we are mapping from RD, not just any kind of metric space, from Euclidean space into RK. And hopefully K is very less than D. And this is called a random projection. And the goal is to preserve the distances as much as possible. And this could be achieved by a good random projection. And the guys in Stanford University are interested in this approach. And of course, we are interested in more general spaces rather than just Euclidean. And in the next 30 lectures, I assume that we only have a general metric. And the metric on the graph that I talk is the shortest path because it is the most natural and intrinsic metric. And the theorem in 1984, when I was 3 years old, a person had a theorem that says for any, assume that k is greater than 4 log n divided by epsilon 2 over 2, epsilon to the third over 3. Then for any set of endpoints x1 through xn in RD, there exists a map from RD to RK such that for any I which is not J, you can preserve the distances up to distortion. It means that the difference is preserved after projection. So this is up to a 1 plus epsilon distortion. So this is in RD norm, and this is in RD, which is our original space. So when K increases, here when epsilon decreases, k increases. So the construction can be done like this. For example, Z is drawn from a uniform distribution in RD, and we defined the projection actually very easily. I do it for R and then I extend it to RK. So for PZ of V, this is just the inner product of your random vector and V. So Z is your random vector, which is in RD, and it is drawn from a uniform distribution. And for the same thing, you can do it for RK. So if you embed your Euclidean space into RK, then you can write it as PZ of V. This is a matrix, but all of these rows, Z1, Z2, up to Zk, are linearly independent. And we just multiply this matrix by V, which is D by 1, and this is K by D. So this is K by 1. And we go to the space of RK. And there is a proposition that says if X is in RD, a fixed vector with norm equal to 1, and consider its random projection, as I said, PV on the random vector. So now V is a random vector. So our notation is changed. Then expectation of PV of X is 1 over D. So the proof is very simple. Without loss of generality, we assume that X is just E1. E1, I mean 1 and then 0. And because it is in RD, we can write the expectation of projection of X like expectation of projection of E1 squared. And this is exactly expectation of V and E1 squared. So this is the expectation of V1 squared. And I want to prove that this is just 1 over D. So to prove this, I say V is a random vector of length 1. So 1 is equal to the length of this. So all random elements are unit length. So this is equal to expectation of J from 1 to D, Vj squared, which is equal to J expectation of Vj squared, and expectation of Vi squared is D. And we are done with the proof. So it was very simple. Now I want to extend it a little more. So I want to say that now your X is in RD and fix X as usual, and consider its random projection on a k-dimensional random space S. And then, so the theorem is this, and we want to prove it. Then expectation of, so we want to prove that expectation of this projection squared is equal to k over D. Let R be a rotation. So this is a rotation that map S. Remember that S is a KD random space. So R be a rotation that map S on the subspace EK. subspace ek is spanned by E1 through ek. And because we know that rotations do not change norms, we can easily show that expectation of this projection is equal to expectation of after applying the rotation to the rotated point squared. And we have defined V is equal to Rx. So the length of a unit vector when projected on a random k-dimensional subspace has the same distribution as the length of a random unit vector when projected on a fixed k-dimensional subspace. So we consider V as a random vector. So, this is the image of a vector under a random rotation. And we know that Rs is Ek is fixed. So you just write expectation of this projection, which is now because we have defined that this is just after rotation of Rx, and this is expectation of P and Ek and you can represent it as the sum over the bases, Vi, Ei, and I said that it spans like this. So Vi, Ei squared is equal to Vi squared, and this is equal to I from 1 to k, expectation of Vi squared, and this is I to k, 1 over d, and because you are summing k of them, so it's just k over d, and they have proved that. And so I need another proposition before I prove the Johnson-Lindenstrauss lemma, which is very important. First, I should talk about concentration around the mean. For example, we have a distribution. This one is not concentrated in comparison to another one, which is highly concentrated around its mean. So both of them are distributions. So this one is not concentrated around its mean, and this one is concentrated. And we have two different types of concentration inequalities, let's say. The first one is additive deviations, and so we decrease it exponentially. It means that the probability that a random variable minus its expectation is greater than equal to epsilon is just less than e to the some constant epsilon. And also we have multiplicative deviation, which decreases exponentially. So we can write expectation probability that u is less than t expectation of that random variable is less than equal to e to the power or e to the constant 1 t, where t is less than 1, and p of u greater than. This is the probability. So these are the tail probabilities. T expectation of V. So it's a rare event. These are less than expectation of minus constant t if t is greater than 1. So the proposition is that for any beta where beta is between 0 and 1, the probability that the norm of projection is less than equal to beta k over d. This is the t that I was talking about in my previous slide. And this is less than equal to expectation. This is less than equal to e to the power e to the k over 2, 1 minus beta plus ln beta. And for beta greater than 1, expectation of projection of x, the probability that this is greater than beta k over d is less than e to the k over 2, 1 minus beta plus ln beta. And in order to prove the Johnson-Lindenstrauss lemma, we first use random projection to Rk. And k is chosen in the theorem. And we rescale it by d over k ps. And by proposition, I say that a vector of length 1 still has expected length 1 after projection. So projection does not change the length of that vector. And then I use the concentration that the actual length will be very close to 1 with high probability. So we say that this projection Rd to Rk, by linearity, we can say that P of xi minus P of xj is equal to P xi minus xj. Zi is xi minus xj. We prove that the probability that norm of P of z squared is greater than equal to 1 plus epsilon, which is our t, times expected value. I proved that it is k over d, times z squared. This probability is less than 1 over n2, n squared. And to see this, we apply the concentration proposition that I showed. So the probability that P of z squared is greater than equal to 1 plus epsilon k over d z squared is less than e to the k over 2, 1 minus plus ln 1 plus epsilon. And we know that ln of 1 plus epsilon is less than epsilon minus epsilon squared over 2 epsilon. And plug in the formula for k from the theorem, we obtain that e to the k over 2 plus 2n 1 plus epsilon is less than equal to e to the 2 log n